I want you to take this in, and I want you to tell any colleagues who you know and are not here about tomorrow's quiz. As I've told you, the quiz is on one of these questions you'll get. Okay? There'll be lots of different questions, and they'll be distributed, so you and your neighbor will probably get different questions, but they will all be questions from this pink sheet, set homework number 6. That's guaranteed. What's also guaranteed is that you have to get the answer correct. Now, you guys are engineers, you'll be taking on responsible jobs. You've been told what it is I expect of you for tomorrow, and I want you to get the answers and get them correct. You must show your work as well, and you can always check. So tomorrow's recitation sessions will begin with 20 minutes of questions from you guys, and you can ask the TA to do any question similar. They won't do the exact same questions as are on here, but they will do similar questions. So you can make up similar questions and ask them if you need help in doing them. But then you will be given 35 minutes at the end of the recitation section or session, and you will be expected to get the answer correct. That means right. Now, you can always check your answers by differentiation. So I want you to get used to doing this. So it's a matter of just knowing your technique, knowing the method, and being careful with your differentiation and your application of the method. And then checking afterwards that you indeed have the right answer. So what did I say?
Make sure you have the right answer.
Right. And the marks will be 0 or 10. 0 or 10. So I want you to make sure you know how to do all these questions. Yes? Number 4. Thank you very much. Thank you very much. There was none given, was there? Now, rather than tell you what it is now, I'm going to put it up on, I'll have that up on D2L later, about 2 o'clock this afternoon, 3 o'clock this afternoon, okay? I'm sorry about that. Thank you for spotting it. You had a question, the gentleman in glasses. Hello, you had a question? There's no graded homework due tomorrow. You will, on D2L, later today, the graded homework, which will be due next Wednesday, like tomorrow week, November the 13th, it will be up on D2L. And I'll bring copies to class on Thursday. Right. Right. Any questions? Any answers? All right. Now, what we're going to do today is the second method we learn in order to solve second order linear ODEs, where the coefficients P and Q may not be constant. In other words, these can be functions of time, and indeed the forcing term will be a function of time in general. But we will demand that the coefficients P, Q, and G will be continuous in the interval of time in which we want to solve the problem. So we will be looking to construct general solutions of 6.1. 6.1 is this equation with G of t, non-homogeneous term on the right-hand side, some given forcing. The related homogeneous problem is when you have 0 on the right-hand side. Now you remember, because the equation is linear, we can construct the general solution of 6.1, namely the non-homogeneous equation, by finding any particular solution. That means any function y of t which solves this equals g of t, together with the general solution of the homogeneous equation. So the sum of those two things is the general solution of the non-homogeneous equation. The first method we learned was for a set of equations where the p and q were constants and the g of t belonged to a special class. It was a linear combination of functions of the form t to 0 or a positive integer power times e to the at times either cos bt or sine bt. So if the right-hand side belonged to that class and p and q were constants, then we use this so-called method of undetermined coefficients, which is what we are testing in the quiz tomorrow. And for those latecomers that just wandered in, let me say again that tomorrow's quiz is all or nothing. The questions will be questions straight out of the pink sheet, set homework number 6, and you are expected to get the question correct. So no little errors, because you can always check your answer. Right, let's go back now and let's revisit. Yes, question.
About that first case where P and Q are constant.
Yes.
And G of T follows that set of rules. The T can't be to a negative power.
No.
But the E to the power can be negative.
E to the A, the E to the AT certainly can be negative. So the A can be, yes. So the question was, in the set of functions that we have to have G belong to for the method of undetermined coefficients, it's functions of the form t to a power times e to the at times cos or sine bt. The b and the a can just both be real numbers. The e to the at cos bt. So the b and a can be any real number. But the power of the t has to be either 0 or a positive integer. So it's a non-negative integer. The reason it can't be, this gentleman asked, can it be a negative integer? The reason is it can't, because when you differentiate that, you will keep on going. You'll always generate new functions. So you will have an infinite space of possible functions that can be spanned by all derivatives. So that's why those don't work. But we'll be able to do some problems and get explicit analytic answers using this method of variation of constants. So let me revisit first order equations. So we'll just revisit dy by dt plus p of ty equals g of t. And the corresponding homogeneous equation will have 0 on the right-hand side. So we'll call this equation 1 and this equation 2. And we'll let v of t be a solution of 2, namely dv by dt plus p of t times v will be 0. Now, we're going to seek solutions of 1 in the form y equals no, I'm sorry, I want to keep notation straight. I made an error in notation here. I want to call this y1. Otherwise, just the notation itself will confuse you. So this is dy1 by dt, and this is p of t y1. So y1 is a solution of the homogeneous equation. So dy1 by dt plus p of t y1 is 0. And now we're going to seek solutions of the non-homogeneous equation in the form y1 times v, where v is unknown, or v is to be determined. Right? If this is going to be a solution of 1 here, well, when I substitute this into the equation, it has to satisfy it. So let's compute dy by dt. So I have dy by dt is equal to y1 dv by dt plus v times dy1 by dt. Now, if I substitute this into the equation, I'll find y1 dv by dt plus v times dy1 by dt plus p of t times vy1 equals g of t. Everybody see that? I just substituted dy by dt in here, and then p of t times y in here, and that's got to be equal to g of t. Now, why was this a particularly convenient form in which to look for the solution? And the answer is, if I just combine these two terms here, let me take the v out. So it's dy1 by dt. I'm factoring out the v. So I get v times dy1 by dt plus p of t y1 equals g of t. So now, what's that equal to? 0, because y1 was chosen as the solution of the homogeneous equation. So that scrams. Now, this is easy to solve. I get dv by dt. Do it in black. I get dv by dt is g of t divided by y1 of t. Yes?
Could you explain why that's 0 again?
All right. Because y1 was chosen to be the solution of the homogeneous equation. In other words, the homogeneous equation is this equals 0. Therefore, dy1 by dt plus p of t y1 is 0. Now, this is very easy to solve. V of t is just the integral of g of t over y1 of t dt plus a constant. And the general solution y then will be y1 times this, y1 times t, g of t over y1 of t dt plus c times y1 of t. Now, you've seen this before, because y1 of t, what is y1? Well, it's just the solution of this equation. It's e to the minus integral p of t dt. It's exactly this is exactly what you get using the integrating factor. The integrating factor for this problem would be e to the positive p of t dt. Okay? But when we go through and solve using the integrating factor, this is exactly the form in which we get the solution. So using the integrating factor to solve linear first-order equations is the very same as using this method of variation of parameters. And we're going to just follow the very same idea when we go to higher order equations. In fact, you will be able to guess after we do second order equations what you have to do third order equations or fourth order equations, etc., etc. Now, you're a very good class, and so, you know, from the questions people have asked, and I know not a majority, but some of you have had matrices and a little bit of linear algebra. How many people have had some vector calculus, linear algebra, matrices? Yeah, okay. I'm going to put on D2L how to write this whole thing when I work with second order equations or third order equations in matrix form. Just because, so that you'll see there's connections with things you've done in the linear algebra. Now, it's not required for this course, and it will not be on any exam that you'll be able to solve matrix equations, but it may be useful for some of you who've come across some of these ideas to see how they apply in the context of systems of differential equations. So that'll be up in D2L in a day or two. Right, now, so this is the scheme. So the scheme we want to use to solve 6.1 is we first of all would like to identify the solutions of the homogeneous equation 6.2. So let y1 of t, y2 of t be two linearly independent solutions of 6.2. Now, in the first order equation, we sought solutions, particular solutions. Actually, it turns out that the particular solution generates you naturally the general solution. We sought solutions of the non-homogeneous equation by looking for solutions in the form the solution of the homogeneous equation times a function that we have to determine. And it proved to be particularly convenient because it turned a first order equation, it sort of got rid of the p of t from the first order equation. It got rid of all this, and then we just a straight integration to do. Question, can we do the same at second order? All right, well, we seek a special solution, particular solution in the form y1 times v1 plus y2 times v2, where v1 and v2 are both functions of time, to be determined. Now, if, for instance, the g of t on the right-hand side were 0, so we're solving the homogeneous equation, then the general solution of the 6.1, okay, oh, yes, 6.1 would be indeed a linear combination of y1 and y2. The v1 and v2 would be both constants. But when we have a non-zero right-hand side g of t, they won't be. Okay, well, let's calculate the derivative. yp prime. It's going to be y1 prime v1 plus y2 prime v2 plus y1 times v1 prime plus y2 times v2 prime. Now we come to the very key step. We were trying to solve for a solution yp of t which satisfies 6, 2. But we've introduced two unknown functions, v1 of t and v2 of t.
Which equation is 6, 2 again?
6, 2 is the homogeneous equation. 6, 1 is the equation as a solution of 6, 1. We want to solve the non-homogeneous equation by seeking solutions of this form, where v1 and v2 are two functions to be determined, and y1 and y2 are the two linearly independent solutions of the homogeneous equation 6, 2. Now, we have a choice here, you see, because we introduced two new functions, v1 and v2, and we started just with one, we can choose a relation between v1 and v2. And we choose that relation to be such that we just make this to be 0. This is a free choice of one relation between the two unknowns, v1 and v2 of t. Now, in the matrix formulation, this sort of just comes out very naturally. But here, it's fair. We introduce two new functions. We're allowed one connection between them. We can prescribe one connection between them. But after that, we have no more freedom. We have to make sure that the remaining combination satisfies the actual equation we want to solve. So now we get the second derivative, yp double prime. This will be y1 prime v1 prime plus y2 prime v2 prime plus y1 double prime v1 plus y2 double prime v2. Now we're going to substitute it into the equation. We're going to substitute these three expressions into 6, 2. And what are we going to find? All right, we'll get y1 prime v1 prime plus y2 prime v2 prime plus, I'll put it here, y1 double prime v1 plus y2 double prime v2 plus p of t times y1 prime v1 plus y2 prime v2 plus q of t times y1 times v1 plus y2 times v2 equals g of t. God, that's a mess. That's a mess. Why is that? Why has that got any advantages over what we started with? Well, let's do a little reorganization of the expression. So this is going to be y1 prime times v1 prime plus y2 times v2 prime plus v1 times y1 double prime. So I'll mark the terms now I'm putting in here. Blue, blue, blue. So this is the blue terms. Plus p of t times y1 prime plus q of t times y1. So that's this term, and that term. Now we'll do these guys. We'll put a tick on the v2s. Let's get them together. So I get plus v2 times y2 double prime plus p of t times y2 prime plus q of t times y2 equals g of t. Now, why is that much simpler than what we started off with? Can anybody see some simplification of that? 1, 2, 3, 4, 5, 6, 7, 8. 8 on the left-hand side and a forcing g of t on the right-hand side. Ryan, what do you say?
Well, from the original expression, y1 double prime plus q y times q ty is equal to g of t, so can you substitute g of t for this?
Absolutely. This is a big fat 0, and this is a big fat 0. Because y1 and y2 satisfy 6, 2, the homogeneous equation. Just in the same way as this guy disappeared when we did a first order equation, a whole pile of terms disappear. And now things are very easy because we first of all have this expression up here. We have now y1 times v1 prime plus y2 times v2 prime equals 0. And then from the actual equation, I have y1 prime v1 prime plus y2 prime times v2 prime equals g of t. Two linear equations for v1 prime and v2 prime. So two linear equations for v1 prime, v2 prime. Solve and integrate. That's it. End of story. Now we'll do lots of examples to show you how this all works out in practice. Yes, question? Very good. Okay. Can I just stress one thing and then I'll come back to your question? The question is, supposing it was a third order system, what would I be doing? Well, we'll address that now after I make these remarks. When we did the first order equation, we ended up with this simple thing. y1 times v prime equals g of t. And then that was easy to solve. As long as y1 isn't 0, then we can divide across and find out what dv by dt is. To find v, we just integrate. Here, we're going to solve two algebraic equations for v1 prime and v2 prime. T is sort of just sitting there in the equations. We're only solving algebraic equations. But of course, when we solve for v1 prime and v2 prime, there'll be functions of g of t and y1 of t and y2 of t and y1 prime and y2 prime. And then we just integrate, straightforward integration. What's the condition that you can actually solve these equations? What's the condition that I need to solve those two algebraic equations? Do you remember when we have a pair of equations, ax plus by equals something and cx plus dy is something? When can we solve those equations? Yes? What's that? The Wronskian is non-zero. The determinant, the coefficient determinant, y1, y1 prime, y2, y2 prime. So I need this cross product. y1 times y2 prime minus y2, y1 prime to be non-zero. That's equivalent to saying that I need the vectors y1 and y1 prime. At any given t, that's a vector in the plane. And the vector y2 and y2 prime, at any given t, that's a vector in the plane. We want them to be non-collinear. Okay, so we require, of course, this requires that y1, y2 prime minus y1 prime, y2 is not zero. That's the Wronskian. How do we know it's non-zero? Because I asked to choose two linearly independent solutions of 6-2, the homogeneous equation. And we know, as long as we're dealing with differential equations, that linear independence and the Wronskian being not zero are the same, as long as we're in a domain I where the P and Q and G are all continuous. All right, so let's do some examples. Any questions? Yes?
This is the method of variation parameters.
Yes. Sometimes people call it variation constants, but so it's okay. Now, so let's solve so I'll first of all solve a problem that you can do by undetermined coefficients, and which we've already done and for which you've got an answer. And then we'll do some harder problems where you don't have methods to solve the equations yet. All right, so d2y by dt squared minus y equals e to the t plus t. Y of naught, I think we took to be 0. Dy by dt of naught to be minus a half. And the solution you've already done is a half t e to the t minus t. Okay. Now, let's get that solution. Now, this is an equation which has the ingredients, namely those coefficients are nice constants, and the right-hand side belongs to the special class of functions we're allowed. So we can solve this by undetermined coefficients. But now we're going to solve it by the method of variation of parameters. Yeah. Okay. All right. So we're going to seek, first of all, what are the solutions, linearly independent solutions of the homogeneous equation? What are they? It's what? Well, one doesn't satisfy the equation. Yes, I know what you meant. You meant e to the plus 1t and e to the minus 1t. Right, so e to the t and e to the minus t. We seek a particular solution then. Seek a particular solution of the non-homogeneous equation yp in the form e to the t v1 plus v2 e to the minus t. We differentiate and we get v times 1 e to the t plus minus v2 e to the minus t. And then the term with the derivatives of v1 and v2. Now, we have one free choice to make. And we can make that free choice, this, to be 0. Now, after that, we're stuck. Now, let me go back to this young lady's question. She said, what would you do if you had a third order equation? Well, then we would be starting with 3 linearly independent functions, y1, y2, and y3. And we would look for a solution in the form v1, y1 plus v2, y2 plus v3, y3. When we differentiated once, we would ask that this be 0, y1, v1 prime plus y2, v2 prime plus y3, v3 prime is 0. Now when you take the second derivative, you have one other free choice because you've introduced three functions, and you only have to satisfy one equation. So one relation between the three functions will be y1 v1 prime plus y2 v2 prime plus y3 v3 prime is 0. The second relation will be when you take the second derivative, you will ask that y1 prime v1 prime plus y2 prime v1 prime v2 prime plus y3 prime v3 prime be 0. And then you will end up with an equation. The final equation, instead of being just this, will be y1 double prime v1 prime plus y2 double prime v2 prime plus y3 double prime v3 prime equals g of t. So then you'll have three equations to solve for v1 prime, v2 prime, v3 prime. And again, the condition they have a solution is that the Wronskian is non-zero. Yes?
Is that, as you increase in order, are you just going to be adding more terms up to an nth order?
Yes,
term?
exactly. Exactly. You follow the same prescription. One of the nice things about the matrix formulation of all this is it sort of does it just in one go. But we don't know matrices, so we stick with scalar equations, which are perfectly good. Yes?
So if you can set those two terms equal to 0, why wouldn't you just choose to set v1 plus v prime of 1 equal to 0?
You mean take another combination?
Yeah, I'm saying why wouldn't you just eliminate one of those constants? I don't understand how you're setting that part equal to 0, I guess.
Okay, all right. When I take the derivative, yp prime, I get y1 prime v1 plus y2 prime v2 plus y1 v1 prime plus y2 v2 prime. Now, it's certainly true. I could choose different combinations, but I wouldn't then get this very convenient relation at the end.
But what if you were to say that y prime 2 v2 plus y2 v prime 2?
Right.
What if you just eliminated those two?
Yeah.
The sum of those
If I took those two terms instead of those two terms and put them equal to 0, yes. I mean, that would be okay, but I would not get any simplification in the final equation. So I'd have as hard a problem to solve when I finished as I had at the beginning. Okay? Very good. Now so we set that equal to 0. Now let's take the second derivative. So I get yp double prime will be v1 prime e to the t plus, minus v2 prime e to the minus t. And then I have plus v1, the derivative of e to the t is just e to the t. The derivative of e to the minus t is minus e to the minus t. So that'll be plus. Okay. Now substitute it in the equation. I get v1 prime e to the t minus v2 prime e to the minus t plus v1 e to the t plus v2 e to the minus t, then minus y, which is minus v1 e to the t minus v2 e to the minus t, and that's got to equal the right-hand side, which is e to the t plus t. Now, why is this simple? Why is this simple? The terms just cancel. Bang, 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 bang. So now I have two equations for v1 prime and v2 prime. Here is one of them. So I have now v1 prime e to the t plus v2 prime e to the minus t. That's 0. And I have v1 prime e to the t minus v2 prime e to the minus t is equal to e to the t plus t. Now, To solve these is very easy. If I add them, I get rid of the v2 prime. If I subtract them, I get rid of the v1 prime. So adding and dividing by 2, I get v1 prime e to the t is equal to e to the t plus t with a half. And v2 prime e to the t, I just get, if I subtract this from this, okay, I'll get minus a half e to the t plus t. And that's v2 prime e to the minus t. Okay? Yes? This is the free choice. This is this free choice that I make when I take the first derivative. I have one free choice between v1 prime and v2 prime. After that, we just have to live with that it solves the equation. Okay? So, v1 prime then, v1 prime is equal to, I've divided cross by the e to the t, so it's a half, 1 plus t e to the minus t. v2 prime is equal to minus a half e to the 2t plus t e to the t. Now we just straightforwardly integrate. This implies that v1 is equal to a half t, and if you just do the integration of t e to the t, it's t plus 1 e to the t, or t plus 1 e to the minus t, and then plus constant. And this tells us that the v2 is minus a quarter e to the 2t minus a half times t minus 1 e to the t plus c2. Okay, let's just go through those terms. First of all, I want to integrate this. Integration of 1 is easy. It's just t. The indefinite integral of t e to the minus t, you carry that out by, what's the method partial fractions. So you'd write this as the integral of t e to the minus t dt would be minus the integral of t times the total derivative d of e to the minus t. Then you integrate by parts, and you just have to then integrate e to the minus t. And that gives you, this is the term that comes out when you're doing integration by parts, and that's the integration of the remaining term. For this one, if I integrate once, e to the 2t is e to the 2t over 2, so that'll give me the minus a quarter e to the 2t. And then again, when I integrate t e to the t, I integrate by parts, so it's t times the d of e to the t, so that'll be t e to the t minus e to the t dt. And that minus e to the t dt just integrates to e to the t, and that gives us that minus 1 there. So the general solution then is y equals e to the t is e to the t times v1, so it's a half e to the t times t minus t plus 1 times e to the minus t plus c1 plus e to the minus t times minus a quarter e to the 2t minus a half times t minus 1 e to the t plus c2. Now, terms come together here. We have here a half times t e to the t. Right, so we have a half times t e to the t from there. Then we get this e to the t by this guy will give me just minus a half times t plus 1. This c1 times e to the t will be just like that. Now here, I don't multiply what? I'm sorry?
So it's that whole 1/2 times everything, and then you have plus.
Oh, that's right. That's right. So I'd have a half in here. Yeah.
So what I
Oh, that's right. That's exactly. Thank you very much. So it's C1 e to the t then, and then that's correct. Thank you.
So if you multiply the constant by C1, because in your V1 you just have it, you're adding the constant.
Right. We just have added the constant V1 in here. So you're quite correct. It didn't come under the half there.
You multiply it by E1.
Yes, because the solution, I'm looking for the solution in the form. I seek solutions V1 e to the t. So when I find V1, I have to multiply it by e to the t. Yeah, and then V2 by e to the minus t. Now, from here, I get minus a quarter times e to the t. Then from here, I get, this gives us 1, so it's minus a half times t minus 1. And then I get plus c2 times e to the minus t. Now, one final step, and I'll write it over here. The solution then, y is equal to a half t e to the minus e to the t. Now these two terms just add to minus t. This term and this term just add to minus t. And then I get plus c1 minus a quarter e to the t plus c2 e to the minus t. Now I've taken account of all the terms. So you see the method gives us the answer. This was our answer here. This is the general solution. So it's the particular solution which we found here, which is the same as what we found here. And then the general solution of the homogeneous equation, you can call this A, and you'd call this B. Because if you have a constant C1, C1 minus a quarter, it's just another constant, which is yet to be determined. So if you write this as your general solution, substitute in the initial conditions, you'll find A and B are 0. So the initial conditions imply that A and B are 0. All right, so let's retrace our steps and walk through all that again. We have an equation in the form of a second order equation with a non-constant, non-zero right-hand side. We look for the two linearly independent solutions of the homogeneous equation. Here they are e to the t and e to the minus t. We then seek a particular solution in the form of an unknown function v1 e to the t plus an unknown function v2 e to the minus t. If we were just solving the homogeneous equation without anything here, we would of course find v1 and v2 are simply constants. When we'd get down to this stage here, we would have had nothing on the right hand side, and v1 prime and v2 prime would both be 0, and v1 and v2 would be constants. Then we differentiate once. We use the degree of freedom we have because we introduced two new variables, v1 and v2, to make this part 0. Having done that, we've no more freedom. Now we just have to differentiate and get what we get and substitute everything into the differential equation, which we have done here. When you do that, one of the nice things is you're going to find, because we've looked for solutions in this form, and we've taken this particular choice of relation between v1 prime and v2 prime, we are going to find that all the coefficients of v1 and v2 vanish, and I'm just left with an equation for v1 prime and v2 prime. Couple this equation with this choice led to this pair of equations here. Very easy to solve for v1 prime and v2 prime, and then integrate. Now when you integrate, you notice certain terms came together, a bit from here and a bit from here, all came together to form the general solution. And that's the way it will turn out in general. Now, this method is a little bit longer to apply than the method of undetermined coefficients. And in certain cases that we like to apply, like the forced damped oscillators, it turns out that you have to know quite a bit of trigonometry when you're doing this integration with the v1 prime and the v2 prime, and then combining it back in this form. This would be a cos and this would be a sine, and then you have to know lots of trig formula in order to get the solution that you would have got slightly more easily using the undetermined coefficients. All right, before I take down this example and start on another, are there any questions? Yes?
Small board question. Over on the, near the bottom right there, where you have the e to the minus t next to the t plus 1 in parentheses.
Yeah.
To the left of that?
Yeah.
To the left of that term.
Yeah.
So you up one line.
Yeah.
To the left. There.
Right.
Is that distribution of the e to the minus t part of the parentheses starting at the t?
Yes, thank you.
Okay.
Yeah. Good. Right, let's try another one. Right, this time, you just see on, okay, so y double prime plus 1 over t times y prime minus 1 over t squared times y equals 1 over t. And we're going to work in the interval t lies between a half and infinity, and we'll give initial conditions at 1. Okay. Right. Now, the first task is we want two linearly independent solutions of the homogeneous equation. Okay, so in other words, this equation with a 0. Can anybody guess one solution? Yeah? T squared. Well, that would make this, so I'd have t squared, so that'd give 1 here, a 2 here, and unfortunately a 2 there. What would be simpler than t squared? T, right. y1 equals t is a solution. Now, if you know one solution in a second order equation, how do you find a second? Remember? Okay, find the second linearly independent solution by reduction of order. And it's very like this method that we have used for finding the solutions of the non-homogeneous equation. We set y2 equal y1, which is here t, times v. y2 prime is tv prime plus v. y2 double prime is tv double prime plus 2v prime. Right? Now, we just substitute it in the equation. We get tv double prime plus 2v prime plus 1 over t times tv prime plus v minus 1 over t squared times tv equals 0. Because we looked for solutions in this product form, all the coefficients of v vanish. And now I'm left with a first order equation in v prime. So this is an equation of t v double prime plus 3v prime equals 0. Okay, let's call v prime u of t. So now this is the equation du by dt, if I divide across by t, plus 3 over t times u equals 0. Integrating factor is e to the integral of 3 over t dt, which is this is 3 log t, so it's t cubed. Remember, t is greater than 0 because we chose to operate in a domain where t is positive. So I multiply across by t cubed, and then this just becomes d by dt of u times t cubed is 0. Because t cubed du by dt plus 3t squared u is just the total derivative of u times t cubed. Yes, question?
Wouldn't there be a t times it? Wouldn't it be t du by dt? Because v prime t is equal to negative t. You got t.
No, I have d2v by dt squared. That's just du by dt. Plus 3 u. That's just u. I divide it across by the t. Right? So now integrating this gives me u times t cubed is a constant, or u, which is v prime, is a constant over t cubed. This means that v is minus c over 2t squared plus a constant. And this means y2, which is t times this, is minus c over 2t plus dt. So, a second linearly independent solution then is 1 over t. Actually, we can make any choice as long as the c isn't 0. But the simplest choice is just have it 1 over t. So, having one solution of the homogeneous equation, you can always get the second by solving a first order equation. So now we're in this nice shape that we have these two solutions. Now we're going to solve the non-homogeneous equation by this method of variation of parameters. All right, so now we seek yp in the form v1 times t plus v2 times 1 over t. Take the derivative, yp prime. It's v1 times the derivative of the t, which is 1, minus v2, the derivative of 1 over t is minus 1 over t squared, plus v1 prime 1 over t, plus v2 prime, v1 prime t, plus v2 prime 1 over t. That's a minus. Now we make our free choice. This equals 0. Now differentiate again. yp double prime is v1 prime minus v2 prime times 1 over t squared plus 2v2 over t cubed. Now we substitute in the equation. So I get yp double prime, which is this, now I have plus 1 over t times yp prime, and then finally I have minus 1 over t squared times v1 t, v2, 1 over t. And that's got to be equal to 1 over t. Question?
Can you go over how you got to 1 over t?
All right. From which state? Are you happy with this?
Yeah, from where you have q equals v prime equals
All right.
c over t.
All right. So I have dv by dt is c over t cubed. If I integrate 1 over t cubed, I get minus 1 over 2t squared, right? The integration rule is up and over. So I get this, and then a free constant. So now I have v. y2 is t times v. So multiplying this by t, I get this. Now I want these two solutions to be linearly independent, different. The Wronskian can't be 0. So as long as I choose the c non-zero, that'll be true. I could choose the c to be 45 and the d to be 3. That's fine. But the simplest choice is to make the c as minus 2 and the d to be 0. Because I prefer not to write minus 200 over t plus 3t as the second solution. Right? I can take any linear combination I like. Okay? So 1 over t is the simplest of the, it's the simplest form of the linearly independent solution. But if you wanted to choose y2 to be minus 45 over t plus 20t, that's fine. You will still get the correct answer if you do the arithmetic correctly. All right. Question?
Could you go over what you did to get the answer in the blue box there?
All right. When I differentiate here, I differentiate a product. I'm going to get two terms, two sets of terms. One is v1 times the derivative of this guy, v2 times the derivative of this. Then the other term will be the derivative of v1 times this, plus the derivative of v2 times this. I have one free choice.
Said the incorrect thing. I meant how you got the 2v2 over t cubed.
Okay. When I differentiated this, the derivative of minus 1 over t squared is 2 over t cubed. T to the minus 2, the derivative is minus 2, t to the minus 3. All right, now what should happen? Look, this guy and this guy and this guy scram. This guy and this guy scram. So now I have two very simple equations. I have v1 prime times t plus 1 over t times v2 prime is 0. And the second equation I get is v1 prime minus 1 over t squared times v2 prime equals, the right-hand side is 1 over t. They're very easy to solve. Let's multiply across by t. Then I get t v1 prime minus 1 over t v2 prime equals 1. So I replace that by that. If I add the two things, so I get t v1 prime is 1. Sorry, 1/2. Because I get two of these equal 1. If I subtract this from this, I find that 1 over t v2 prime is equal to minus 1/2. So this tells me that v1 is 1/2 log t plus c1, because v1 prime is 1 over 2t. I don't have to put in the goalposts because we're t positive. This tells me that v2 is equal to minus 1/4 t squared plus c2. So now combining those, I get yp then is t times v1. v1 was what? v1 was 1/2 log t plus c1. And then I have plus 1 over t times v2. v2 was minus t squared over 4 plus c2. Okay? So this becomes 1/2 t log t. Then I have plus c1 minus 1/4. Turns out the same. T plus c2 times 1 over t. v2 prime is negative 1/2. When I subtract these two things here, I get 2 over t times v2 prime is 0 minus 1. Okay, so multiplying across by the t here will give me v2 prime as minus 1/2 t. Okay. And you see, this is the general solution. We can call that A, and we can call this B. This is the linear combination of the two linearly independent solutions of the homogeneous equation. And this is the particular solution, 1/2 t log t. In other words, if you differentiate, just shove this into this equation, it'll satisfy the non-homogeneous equation. Now, there is nothing like practice. So this is spelled out, this method is spelled out very clearly in the notes, lectures 16 through 21. There are several examples, and I'm going to give you another example here that we'll start with next day, but I'd like you to try before we get there. So it's the same as this, almost. Y double prime minus 1 over t y prime plus 1 over t squared times y equals, and we'll put on the right-hand side now, t. And we'll again work in the region, so the interval I will be where t is positive. Question?
You don't, to like solve for y1, you don't want to like guess?
Yes. Good question. Good question. In general, with t-dependent coefficients like p of t and q of t, there is no simple algorithm for finding what the solutions are. What happens in practice is that we can make a good guess, or we can actually, there's ways of approximating solutions by series. You write down a Taylor series for the solution, and you use the equation to determine coefficients. So there are practical ways in which you can actually get the y1 and y2. For all the examples we'll be doing this class, we'll be able to either guess one solution or I'll give it to you. All right, don't forget, tomorrow's quiz is 10 or 0. You get it right or wrong.